So now that we know the postulates of relativity and starting to absorb them, we can look at some of the effects of this. This is the main one. You can sort of derive all the rest of the stuff from this. Time dilation. Okay. So I have a little blurb there that, right, the speed of light is constant. That's really what this comes from. And so we're going to, just a couple quick definitions at the front here. We have the proper time, and you'll notice that it's denoted TS. So basically we're using S for stationary. So if you are measuring something that is stationary in your reference frame, so we're assuming for special relativity, right, people are in inertial reference frames. That is, reference frames that are not accelerating. Okay? So if you're measuring something in your inertial reference frame, right, even if, well, we'll look at a couple details, but that thing is, we're going to say that's TS that you're measuring, right, the stationary time. If you're measuring something that is moving relative to your reference frame, so you're looking at somebody else in their reference frame that's moving relative to yours, then we'll deal, that says we're dealing with relativistic time, and we will use a subscript m for moving. I say that half in part to convince myself of that, because I always forget that, and I want to call the proper time, I want to put TP, but I got to try to remember we use TS for stationary and moving. So even if you have like these observers here, right? Remember observer 1. So observer 2 is measuring something in observer 1's reference frame. So that would be the moving time or relativistic time. Okay. So I set this up as an example because it basically derives the equation that we really want, right? So we've got observer, and then we're taking a little liberties, but bear with it. Observer 1 on a very fast trolley car, believe me. They're moving at some speed, less than c, but close to it, let's say. So they've got a light clock here. And what a light clock is, essentially, is something that uses light, or the speed of light, to go from the floor to the ceiling and then back again to time things or events, right? So this person is sitting here in their reference frame, and they see light go from the floor to the ceiling and then back down again. Now we want to know how long does that event take for observer 1, right? And then we want to figure out how long does that event take for observer 2, who sees this person and the trolley car moving with speed v, right? And this is where what's going to come into play here is the consistency of the speed of light. Since they both see this event happen and they both see light move at the speed of light, that's going to change how long observer 2 says this takes to happen, right? They're going to see the same thing happen in some sense, right? They're going to see light go from the floor to the ceiling and back down, but they're going to disagree on how long it takes for this to happen. Okay, so we can look at observer 1's perspective, who's stationary, who's in this inertial frame where this is happening. So yes, it's a light moving, but again, because they're measuring something that's stationary relative to them, that is, the ceiling and the floor are stationary in their reference frame. So that means the time, well, time, as you know, is just distance over speed. So the distance that this light travels is 2d. We're calling, right, this distance d, so it goes up and then back down again, and it does it at the speed of light, so that's the c. And then all I did over here was rearrange this for d, right? Multiply or divide both sides by 2, multiply both sides by c, and you get that. And we can just tuck that in our back pocket. Then we can look at observer 2's perspective and say, well, for observer 2, they see something a little bit different. They see light, because observer 1 is moving, right, with this speed v, they see the light actually go up on an angle and then back down, right? That's the path they see light take. So to represent that path, I could have drawn it over here, but you can see basically what we're saying is, well, we know this is d here, right? That's the same D it was. And we can say this length right here, again, C represents the speed, so we'll call that length Z. So this triangle here sort of represents the path of light. It goes up on this angle Z, and then it goes down to the floor the same distance Z. We're assuming, of course, that this speed is constant, that the trolley car is moving. Right, so I've indicated D here, and Z is that distance. If we look at this distance on the base here, right, how far does this trolley car go in the time it takes light to do that? Well, we know distance is just velocity times time, right? So if it's going with speed v, and note though, we're using the subscript m for moving time, right? Because this observer 2 is measuring something that's moving, right? The light is moving on a reference frame that's moving relative to them. So they're measuring the relativistic time for this event, which is for light to go up and down. And then all you got to do is take half of that distance, and we got ourselves a nice right triangle here. And then we can use that right triangle and express that as like Pythagorean theorem. That's all it is right there. Z squared equals VTM over 2 squared plus D squared. And then we can do a little bit of substitution. So over here on the right, I'm just saying this in a general case, right? We know distance is velocity times time, right? So using that, we can say, well, we know that the distance that light travels in observer 2's perspective is 2z, right? That's this distance here plus that distance there. And that equals the speed of it's going to go at the speed of light, that's c, times by the time. But in this case, we'll just be sure to include that subscript m because it is the relativistic time. And we will also, we'll take that and we'll sub that in for z, or technically, I guess we'll divide both sides by 2. So we get an expression for z, and then we can take that and sub it in here. So that's what's written right underneath that. And then we'll also take this d that we found up there and sub that in here. All right. So that becomes CTS over 2. And then it's just a little bit of math, right? We know that everything's squared, so to bring this 2 inside the bracket, right, everything gets squared. The C gets squared, TM gets squared, 2 gets squared. But also there's a 2 squared, technically, on the bottom of everything, so we can just cancel that out, right? Just multiply everything by 4. Then, if we get to this next line here, we can divide everything by c squared. Right, so then it cancels there and there. And then I think all I did here is I took this term here and subtracted it from both sides. So that's why in the next line that term appears on the left. And then factor out the tm squared. That leaves you with this bracket here. Divide both sides by that bracket, which brings it down to the denominator on the other side. And finally, because you want an expression for tm, not tm squared, take the square root of both sides. So the ts squared becomes the square root of that, which is just ts. And you end up with this other term on the bottom. And note what that actually means. Note this, really amazing equation. Oh, it won't do a... All right. Right. What this actually says is the time that observer 2, standing over here, measures for this event. Sorry, give it a second. There you go. The time observer 2 measures for this to happen is different, right? Observer 2 says, like again, suppose observer 1 standing here looking at this happen says, oh yeah, it took 1 second, right, for light to go to This would have to be a very, very big, trolley car for it to take a whole second for light to go up and back down, but suppose it does. So the observer 1 says that took 1 second, right? Observer 2, though, says, no, that didn't take 1 second for light to go to the ceiling and come back down. And it didn't go straight up and down. It followed, it followed this path. It went on an angle because this observer was moving. And they might say, no, that actually took 7 seconds for this to happen. So they would disagree about the amount of time. And this is where we then have to go back to the other postulate of special relativity, that is, there is no correct reference frame. You can't say that, no, observer 2 is correct, right? Observer 1 just doesn't know they're moving. It's like, no, if you are observer 1 and you're in that reference frame, it takes 1 second, and you are correct that it takes 1 second. If you are observer 2 and you are in observer 2's inertial reference frame, right? It's not accelerating either. And you see observer 1 go by, and you'd say, no, this event took 7 seconds to happen, or 14, or 2, or whatever the number happened to be, based on the speed. And you would also be correct. But no one is more correct than the other. And again, if you want to tuck that equation away or remember how to use it, then, that's what we end up with. So I think I made a note here. Because your first thought might be, well, wait a minute. Are you telling me that, people appear to move in slow motion when this is happening? And the answer is yes. Oh, one other thing I didn't mention, just to really get the point across about the consistency, right? Suppose this happened the other way, right? Suppose observer 2 has a light clock here, right? Has a, standing on a little car here, and light here goes up to some ceiling and then down, right? You would have the exact same effect. So observer 2 would say, no, light takes 1 second to go up and back down, but observer 1, who's passing by at speed v, but remember, from observer 1's perspective, observer 1's not moving, right? From observer 1's inertial reference frame, they're stationary, and it's actually observer 2 that's moving the other way, right? Observer 2 would just appear to be going with speed v in that direction. So they would see the exact same thing, and so both people actually see each other moving in slow motion. And that's just the way it is. As weird as that seems, they both see the other. So if observer 2 has a clock here and observer 1 has a clock here, they both see each other's clock moving in slow motion. Now, we'll look at how you sort of square that circle in a bit, but one thing to note here, the speeds necessary to notice time dilation, because this might seem a little inconsistent with your everyday experience. So if you take a speed such as 50 meters per second, right, and you substitute that into this equation, right, you end up with this ratio of Tm to Ts, which, in other words, this is how much longer this event seems to take for someone who sees you moving, right? So you've got a ball, or let's say you've got somebody going by in a car at 50 meters per second, which is, pretty fast, about 170 kilometers an hour. How much slower does time seem to go for someone if you're watching someone go by in the car, right? And they've got a clock. And the difference, as you can see here, is very minuscule, right? You would see their clock going a little bit more slowly. So if some event goes on in this car, they would say, no, that event took exactly 1 second, right? You would say, no, actually it took a little bit longer than 1 second. It took, well, you can see the number. I don't want to say all the zeros, but as you can see, the discrepancy is minute. So if you get a dynamics problem and you're dealing with regular, everyday Earth speeds, then just do regular dynamics, right? But if you get something where the speed is very, getting close to the speed of light, then you have to change your equation, right? So understand this is the real equation, but generally you can kind of forget it when you're dealing with regular speeds. And I just copied this diagram from a textbook that just kind of shows you the what's really necessary, right? So that is, take a number, like even 0.2, the speed of light, just 20% the speed of light. The difference you can see here is pretty minuscule. Like Tm over Ts is still pretty much 1. I think earlier, just for fun, I punched in a number like here would be like 0.14. So 14% the speed of light would be enough to go around the Earth in 1 second, right? If you had some sort of device that would do that, and then the difference is just a hair under 1% difference. So you'd have to be going that fast just to notice time taking 1% more slowly. So it's fast before you notice this effect. And to sort of, we won't get into any math with this, obviously, but you might sort of start to think, wait, this seems a bit paradoxical. That is, it seems to lead to some sort of inconsistency here, right? Like here, I'm showing you these clocks. I'm saying, well, observer 1 sees observer 2's clock moving slower. But I'm saying the same thing happens for observer 2. So you might wonder, how is that possible? How can they both see each other moving in slow motion? Shouldn't somehow somebody agree? And one of the things that comes out of this is this sort of twin paradox, right? And the idea here is you've got twins, right? And one of them goes in a spaceship and travels near the speed of light. The other one stays here on Earth, right? Just ages naturally. And then the person in the spaceship returns to Earth. Which one has aged more, right? If the one who had gone into the spaceship went past Earth, could have gone past Earth a couple of times, traveling near the speed of light, like 0.999 the speed of light or whatever, right? They would have had this effect. They would see each other aging more slowly, right? Moving in slow motion. So how do you figure out which one is actually older? And what happens here, though, is it's actually the acceleration that makes this change work out. So in this case, it would actually be the one in the spaceship who ages less, right? So I'll write this, but the word because here is kind of important, right? The twin in the spaceship ages less because of acceleration. And that actually took Einstein probably about another 12 years or so after he published special relativity. That's what we're kind of doing to really deal with situations like this where you have accelerating reference frames, right? Everything we're dealing with, there's no acceleration. Both of our observers were in inertial reference frames. If you want to look at how something like this would actually happen, or like which twin would be older here, then you've got to deal with general relativity, referred to as general because it's more general. Special seems like it's maybe bigger, but it's actually a special case of relativity where you've got inertial reference frames. So you'd have to deal with, and that would actually make everything work out mathematically. But like I said, it gets a little trickier there. Another neat thing with accelerating reference frames, GPS satellites in motion with respect to Earth, typically about 4,000 meters per second. If you remember, we did some of that dynamics. This means they could lose accuracy every day if special relativity isn't accounted for. They would gain about 7 microseconds per day. So that's kind of, if you're looking at some evidence of, again, the effects are really small when you look at this, but it would add up, right? And if you look at something like clocks, that would work out to them losing like kilometers over, several days or whatever, because they depend on so much precision, right? It's all about with GPS, right? It's all about, you've got multiple satellites, let's say, and you've got someone down here, right, with their little GPS in their hand. So how that thing works, right, is it looks at all of these satellites, which are represented by these little dots, right? They've got very, very precise clocks on them. And so the whole idea is they keep broadcasting these time signals, and the GPS device looks at the time it gets from each of these satellites, right? And looks at the difference, and then it can figure out how close am I to each of these satellites, and from that figure out where it is. But if these clocks are running at a different speed, and they are, and you don't take that into account, these things would get pretty inaccurate pretty quickly. The interesting thing, though, and it kind of goes to the twin paradox, I said if you didn't take special relativity into account, right, they would lose 7 microseconds a day. But they would lose about 45 microseconds per day because of general relativity. Right? And so that actually turns out to be a bigger deal, being in an accelerating reference frame. Did you know you're in an accelerating reference frame? Now, how do you know you're in an accelerating reference frame? Assuming you're standing or sitting there, do you feel force, like on your feet or your butt or whatever? Do you feel like you're being pulled down? Right? That means you're accelerating. And another way to sort of think about that is, suppose you didn't know, suppose you walked into what you thought was some really, really big building, right? But it's actually a spaceship, and you're inside there, and this spaceship, here's this big building you think you're in, it goes way, way, way out into space. Or maybe they just beam you to the thing. Maybe some advanced civilization has like beaming technology. And they send you up to this spaceship that, it's got some rocket thrusters here, which I'm not going to be able to draw very well. This is a rocket thruster. There you go. Rocket. And what happens, though, is this spaceship that you're in, right? And you're surprised to learn this, of course. But this thing is accelerating at 9.8 meters per second squared, right? It gets it gets an extra 9.8 meters per second faster every second. It accelerates. Do you think you would have any idea that you're actually in a spaceship that's accelerating at 9.8 meters per second? Do you think it would feel any different than while you're sitting here on the surface of the planet? Right? You would have no idea. Again, they beam you up here. You think you're just in a mall or something. You have no idea. It looks the same. They make everything look just like it would. You'd have no idea. You'd feel the same force, right? And so that's really the challenge here. We're not actually in an inertial reference frame. We're in one that is accelerating because of gravity. It's not super fast, right? I mean, relative to how fast it could go, it's not really fast. But if you try to look at effects like this, though, right, with like GPS and that, will actually be cut relative to where the satellites are. We experience time more quickly than them because we're accelerating more. We're closer to the center of the Earth. Okay. So here's one where I guess I already somewhat did this, right? How fast would you need to go so that everyone on Earth seemed to slow down by 1%? And I guess if you were in a spaceship going by, they would look at you and say, oh, you're going 1% more slowly. Right? So what that means, if you're going everyone's going to slow down by 1%, right? That means that, right, this factor here, Tm over Ts, right? Sorry, this thing's writing really slow. Would have to be, right? Well, Tm is 1% slower, so this is like 1.01 over 1, right? If you suppose TS is 1 second, then TN, the moving time, right, the relativistic time, has got, 0.01 extra seconds on it, right? And we have an equation for that now. We know that that has to equal 1 over 1 minus v squared over c squared. I sometimes just write that as like v over c all squared, right? Because it's squared over squared, so sometimes that sort of gives you a sense of what that number is right there. In this case, you can multiply both sides by this square root thing, divide both sides by 1.01, and so that gives me and then we can square both sides. And that means 1 minus v over c squared. And jumping ahead and doing that, I get 0.980296. And then let's subtract 1 from both sides. And that leaves me with negative v squared over c squared equals negative 0.0197. Now they're both negative, so multiply both sides by negative 1. Multiply both sides by c squared. And we get v equals 0.0197 c squared. But of course we'll square root both of that. And so v, just to write it this way, because I feel like having that sort of out in front with a c sort of gives you an idea of that. And square root the answer. That gives me, as sort of predicted, v equals 0.14. And if you want that as a times by 3 to the exponent 8, 4.21 times by 10 to the 7 meters per second, I'm going to say. So really, 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 really fast. To me, it's almost easier just to think of, right, like 0.14. Like I said, that's this number here, 4.2 times 10 to the 7 meters, is about the different, or the circumference of the Earth, like sort of about an average. So if you could go around the Earth in 1 second, then you'd see this sort of time dilation of about 1%. So they said it's not much.